Okay, so if you've been building any kind of modern, real-time application lately, you already know that scaling your compute power is really just half the battle. The actual headache, managing data and memory at massive scale. Today in this explainer, we're unpacking a really fascinating piece of source material, the GitHub documentation for a highly anticipated project called Rivet Actors. And as you'll see, we're looking at what is essentially a total paradigm shift for stateful workloads. To really grasp why this matters, I want you to think about this for a second. How do you actually scale an AI agent for 1 million users? Think about it. If you build an AI assistant, it literally has to remember the context of your conversation. Now, if 1 million people are talking to their own individual assistants at the exact same time, traditional infrastructure starts to sweat big time. You're dealing with this massive overhead just to keep 1 million tiny memories active and instantly accessible. It's a huge hurdle. Okay, let's dive into this. First off, what are we talking about here? When we say stateful workload, we just mean applications that fundamentally need to remember things, or state, across continuous interactions. It's like tracking the cursor positions of 5 different people editing a collaborative doc, or an AI agent tracking a really complex, multi-step workflow. This isn't just a simple request and response web page. The app actually has to actively hold on to the context. So here's our roadmap for today. 1. The stateful workload problem. 2. Enter Rivet Actors. 3. Infrastructure showdown. 4. 0-millisecond latency. 5. Real-world use cases. And 6. The open source future. Let's get into it. Section 1. The stateful workload problem. Look, before we can really appreciate the solution, we've got to understand the intense friction developers are dealing with right now. The core issue highlighted in our source material is pretty simple. Traditional infrastructure just wasn't built for this. It's way too heavy, it's way too slow, and honestly, it's far too expensive to keep tens of thousands of individual states active all at once. If you just need to maintain the memory for a lightweight AI agent, spinning up an entire virtual machine or a massive container is totally overkill. You just end up paying for idle resources you aren't even using, and the whole system slows to a crawl. Which brings us to Section 2. Enter Rivet Actors. Rivet Actors are basically a brand new primitive built from the ground up to solve this exact headache. According to the docs, an actor is a long-running, lightweight process. But here is the absolute game changer. The state lives right there in memory, and it has automatic persistence. That means you can literally spin up one dedicated actor per AI agent, per user session, or per document, and it natively handles its own memory, storage, and networking. It just sleeps when it's idle, and it wakes up instantly when you need it. Section 3. Infrastructure showdown. Now, what's really interesting about this data is the sheer contrast. Conceptually, lightweight processes sound great, sure, but put them head-to-head with industry standards like Kubernetes and VMs, and the numbers from the Rivet developers are pretty wild. For memory per instance, your typical Node.js Kubernetes pod idles around 50 megabytes. A virtual machine, at least 512 megabytes. A Rivet actor is roughly 0.6 kilobytes, literally a fraction of a fraction. And check out the idle cost. Because Rivet actors scale completely to zero on a serverless platform when they aren't being used, your idle cost is exactly $0. Compare that to the constant, ongoing upkeep costs of Kubernetes clusters or VMs. But I want to pull out this specific metric for a second because it's kind of mind-blowing. 20 milliseconds. That is the cold start time for a Rivet actor. And as the source points out, that doesn't just mean spawning the process. That actually includes durable state initialization. The actor is fully ready to go, memory completely intact, almost instantaneously. Now contrast that tiny 20 milliseconds with this, 6 seconds. That's roughly how long you're waiting for a standard Kubernetes pod to do a cold start, pulling the image, setting up the runtime, launching the container, the whole shebang. In the world of real-time collaborative apps or conversational AI, making a user wait 6 seconds just for the system to wake up, that's an eternity. It's a massive friction point that Rivet just completely bypasses. All right, Section 4, 0-millisecond latency. So startup speed is great, but what happens when these systems actually need to read or write data? And this brilliantly illustrates why Rivet's architecture is so fast. When an app queries a traditional database like Postgres, you might see around 5 milliseconds of network latency. Even with a blazing fast in-memory cache like Redis, you're still paying a 1 millisecond penalty over the network. But because Rivet co-locates the compute and the state right next to each other using co-located SQLite storage, that network round trip just doesn't exist. The read latency is technically 0 milliseconds. It's instant. The documentation describes this as one primitive that adapts to agents, workflows, collaboration, and more. And the real beauty of this approach is that you aren't sacrificing utility just to get that 0 millisecond speed. Because it's so incredibly lightweight, it scales horizontally across a global edge network infinitely, but perfectly scales back down to 0 when it's just sitting idle. Moving on to Section 5, Real-World Use Cases. Let's ground this in reality for a minute. Who is actually going to use this? Well, the source highlights a few key areas where this tech totally shines. First up, AI agents, giving every single agent its own persistent memory and context. Then you've got sandbox orchestration and managing those really complex multi-step workflows where you absolutely need durable state at every single step. It's also dead perfect for real-time collaborative documents, literally one document acting as an actor, broadcasting changes out to everyone. You could even use it for highly isolated per-tenant databases or instant multiplayer chat rooms where the room itself is the actor holding the history. Finally, Section 6, the open source future. Now, adopting any fundamentally new architecture is scary if it locks you into a single company's ecosystem. Nobody wants to be trapped. The creators of Rivet clearly know that vendor lock-in with proprietary cloud services is a huge deal breaker. To solve this, Rivet is released under the highly permissive Apache 2.0 open source license. As the documentation proudly states, this actually gives you ownership of your infrastructure. You get true cloud portability and the complete freedom to deploy this exactly how your enterprise needs it. Because it's open source, your deployment options are super versatile. You want to use it locally in development? Just pull it in as a library with a quick npm install. No servers required. If you want to run it in production yourself, you can completely self-host it with a single Rust binary or a Docker container. Or, hey, if you don't want to manage infrastructure at all, you can just deploy it to Rivet Cloud, which is their fully managed global edge network. You got options. So I want to leave you with this final, somewhat provocative thought. Looking at the sheer speed, the absolutely microscopic memory footprint, and the total elimination of network latency we've talked about today, are we actually moving past traditional containers for modern AI infrastructure? Rivet actors make a really compelling case that for highly stateful, real-time, AI-driven apps, the old way of relying entirely on heavy VMs and pods might honestly just be slowing us down. It's a massive paradigm shift, and definitely one to keep your eye on. Thanks for hanging out with me for this explainer, and I hope this gives you a completely fresh perspective on the